that I mentioned that in the exam review, but yeah, this is the equation that is I equals I0. What, can you read it off for me?
I0 exponent of alpha NF in parentheses E minus E naught over RT.
There we go. Thank you. So this is called the Toffel equation. Does this describe a thermodynamic quantity or kinetic quantity? Describes current. What's current? Thermodynamic or kinetic? Kinetic, right? So this describes a rate, which is a function of this over potential right here. So that's just something for you to remember. We talked a little bit about it in class, but I didn't dwell on it in the exam. We didn't have any homeworks on this either, so it probably won't be on the exam. Yeah?
For the pour box diagrams.
Pour bay. Yeah.
Jeez. Maybe later we can have a classroom a lot.
For those.
Come on.
Okay. I know what you're saying. Go ahead.
How do you determine different phases?
Oh, okay. So those are theoretically described phases. So what they do is you have to figure out for each pH and potential, you have to do the calculations for what's going to be in this box. So we didn't talk about how these are calculated. You use the Nernst equation sometimes. You also figure out what the delta G is for specific reactions. And so there's a way to calculate what phase you're going to have where on this Pourbaix diagram, but we didn't talk about it. We only talked about, say if this is iron hydroxide, here's iron, here's Fe2+. We only talked about interpretation of the plots themselves. So that's what you need to know in the exam. Let's say Fe3+. You don't need to know that this box is FeOH2. We didn't talk about how it's calculated, but you need to know how to use the diagram.
Yeah, like what kind of questions would you ask on it? Like,
yeah, I would ask at pH 6 and a potential of -2, what do you have?
oh, okay.
Or I would ask if you take iron and expose it to potential of 3 and pH of 6, is it going to corrode or not? Things like that.
How would you determine that if it's going to corrode or not?
You look, so if I say, let's say pH of 10 and potential of 3, and if I said you take iron is Fe0, and you expose it to a potential equal to 3 volts and a pH equal to 10, I look at my diagram, and these intersect in this Fe3+, and I need to decide from going from Fe0 to Fe3+ has iron corroded. So what do you think? Have I corroded iron when I'm making Fe3+? Yes. Yeah, right? To go from Fe0, Fe3+ plus 3 E minus, this is an oxidation reaction. It's anodic oxidation, and so I know I'm going to get corrosion there because I'm basically taking iron and making Fe3+, which is a corrosion reaction. Now, if here's -2 volts right here, bless me. If I'm in this region, and I say, does iron corrode in this region? No, it doesn't. I still have iron, right? I start with iron, I end with iron. So I'm really asking you about how things change going from one box to the other. So you need to figure out, A, what phase you're in, and is this a product of corrosion? Or is this a good oxide? Is this something else? What's going on? What's going on with this species right there? Yeah.
It's like on the lines in equilibrium, right?
Yeah. So we didn't talk about exactly what these lines mean, but these lines are equilibrium equilibria between these phases. I'm not going to ask you any questions about things on the line.
Every single time it's online?
Has to be. That's the definition of a line in a phase diagram. So if you're on a line, you're at equilibrium between the two phases it separates. For any phase diagram, and you guys will learn more about that as you go on. Yeah?
On the last homework, you had K dispersion and K equilibrium on there. I wasn't sure how that fit in everything.
Yeah, so that is a, I think it was K dissolution. Was it DISS? Yeah. So that's just to remind you that a lot of these concepts that we're talking about, K equilibrium, K dissolution, K solubility product, these are all equilibrium expressions that tell us we have K forward here, we have K reverse here. What's the relationship between K forward, K reverse, and KEQ? Yeah, equals KF over KR. And of course, these are just equilibrium constants for a dissolution reaction or for a precipitation reaction or something like that. So what does equilibrium constant have to do with E0? How do we connect the equilibrium constant to the standard cell potential? What is KEQ related to? It's related to Q, but what's the more important thing it's related to? Delta G, right? Delta G is, what's that? Oh, delta G0 is? R negative RT over, what is it?
Negative RT ln K.
Negative RT ln Q, or ln K in this case, right? Okay, that's great. So here's one expression for delta G0. So how do we relate the equilibrium constant to E0?
There's another relationship. DG0 equals NF.
That's right, and we have delta G0 equals negative NF RT, negative NF, sorry, I'm getting myself confused here, E0 cell. So we have delta G0 equaling these two quantities, and so we can just set negative NF E0 cell equal to negative RT ln Q, and now we can relate the equilibrium constant to the E0 cell. So this is a good point to just remember. That's why I just threw that random problem in on the homework so we could discuss. If you know E0 cell, you know something about the equilibrium constant. If you know something about the equilibrium constant, you know something about E0 cell. So if the equilibrium constant is big, is E0 cell large, small, zero? So say we have a large equilibrium constant. What's E0 cell? Large and positive, right? Because delta G is going to be large and negative for a large KEQ. If KEQ is very small, that means the reaction's not going to be very favorable, right? And so what's E0 cell going to be for a very small equilibrium constant? It's going to be negative, right? It's not going to be thermodynamically favorable. And so this is just a good discussion we're having based on that homework problem, that now, because we can relate KEQ to delta G0 and delta G0 to E0 cell, we can relate these two. And there's an important slide in your notes on that, how we relate those three quantities. Does that cover it? Yeah? So, and the only thing is that K dissolution is, say A is a solid, going to A, say, aqueous. So we would have K dissolution here, Or for something that has, say, A plus B in the aqueous phase, goes to C solid, we might have a K solubility product here, telling us how soluble this is and whether the reaction is favorable in this direction and KSP is high, or whether it's favorable in this direction and KSP is low. Other questions? Yeah.
Does the expression on there with the KEQ equals KF over KR, is that related to the voltage efficiency? Where it's the E cell with like E reverse?
This isn't quite, so this is at equilibrium, right? So the voltage efficiency is when you're trying to drive reactions one way or the other. And that's really not at equilibrium, right? So if you run a cell at E0 cell, how much reaction are you going to have if you try and run a battery at its equilibrium potential? Not very much, right? No reaction happens at the equilibrium potential. So the voltage efficiency basically tells us if we want some current out of this, how high does the voltage have to be, or how low does the voltage have to be away from the equilibrium potential in order to get current to flow? And that gets into the kinetic part, right? So you have to add some overpotential to get the kinetics to go. Yeah.
How much of a distinction should we make between oxidation and corrosion? Can we use the terms interchangeably with respect to like how they die?
Yeah, well, oxidation is exactly one thing, right? So oxidation is some reaction where a metal or anything loses an electron, right? So that's exactly defined. Corrosion, at least in the cases that we've studied, usually involves some sort of metal oxidation. Now, there's a difference. So oxidation, and don't get this wrong on the exam, A goes to A plus,